So today we're going to be solving paper 6, October, November 2025, paper 63. So let's start. Okay, so a student uses the apparatus shown in figure 1.1 to show that water is formed as one of the products when a fuel is burned. The gases produced when the fuel is burned are passed through the apparatus using a suction pump. Now this is the apparatus. We have burning fuel, which is passed through a delivery tube to something called a U-tube, and that will take that gas and then it gets converted into a solid, and then to the suction pump the gases are passed out. So the ice is being used to make this into a solid. So what is the name of the apparatus named W? Now, first of all, we need to identify that this is an inverted funnel. If you see that, this is an inverted funnel. How do you know it is a funnel? Now, a funnel actually looks something like this. This is how we know a funnel looks like. But if you invert this thing, when you invert it, it kind of looks similar to what we're looking at right now. So this is a funnel, and this is an evaporating dish where we're heating or burning the fuel, and then that those gases are passed through the U-tube. So we will name this apparatus as funnel. Okay. Then we have when the fuel is burned, the steam passes into the U-tube. So just why the U-tube is surrounded by ice. Now, why is this surrounded by ice? The main function. Okay. Now, why were we using ice? Now we know that ice in chemistry is used to cool down things. Now, when we're passing something through a U-tube, like we're passing this burning fuel through the U-tube, it's getting cooled down. So we're basically cooling it. So we're gonna write to cool or to condense. To condense steam. This is what we're doing. This is how you can explain it. Why we're doing it? To condense steam so then it can be converted into a solid, which is called a solid X, which we'll find out soon. Water causes solid X in the U-tube to change color. We learned about two types of salts, which was in our Igcse syllabus, which was, first one was anhydrous, copper 2 sulfate. This is the first salt we learned about. Second one was anhydrous cobalt 2 chloride. This is the two types of salt we were required to learn in our Igcse syllabus. Color changes were from white to blue crystals. Okay, now the student tries to use the apparatus figure 1.2 to pass the gas through acidified aqueous potassium manganate 7. Now, as we know, potassium manganate 7 is a oxidizing agent. We know that it is an oxidizing agent. Okay, and we do know that it changes from purple to colorless. Now let's see what this question is asking. There is an error in the apparatus figure 1.2 so that the gases produced will not pass through the acidified aqueous potassium manganate 7. So there is an error in this apparatus, and the gas of the burning fuel is not passing through that liquid. How do we know that? Now look, as we know, whenever you have something like that, your delivery tube should be longer. It should touch the liquid. Then only the gases will go into that liquid. Otherwise, they will just escape through the suction pump. So this should be longer, right? So this is the error in the apparatus. All right, we noticed that. Now the item of the part is labeled Y. Now this is a boiling tube. Pretty easy, no explanation needed. Boiling tube. This is the answer. Okay. Now draw a circle around the error in the apparatus. As we know, we found the errors. We're just gonna draw a circle here. That's enough. No need of a big circle though, but okay. That's fine. And let's go to the next question. The error in the apparatus figure in figure 2.1 is corrected. The student observes that acidified aqueous potassium manganate 7 changes from purple to colorless. Now, state why this change occurs. So one of the things is that this is not a theory paper. So when we're solving a paper 6, you always need to keep in mind is that you're linking it to the practical thinking, not the theory thinking skills. We know that this is an oxidizing agent. This is why it's causing a color change. But you don't need to write that. What you're going to do is go to those quantitative analysis notes you get at the back of the page, and you're going to look for the gas that makes it, right? So the gas which is called sulfur dioxide. Now the sulfur dioxide turns acidified aqueous potassium manganate 7 from purple to colorless. So this is the gas which is actually causing this. So you need to remember the theory part, practical part of this. So you're going to write because SO2 gas is produced. That's all. Just keep ahead of the number of marks you get. So no need to explain a lot for a mark. Okay. Let's go for this one. A student investigates the temperature change when a 5 centimeter length of coiled manganese ribbon reacts with excess dilute sulfuric acid. So we have an acid which is sulfuric acid H2SO4, and we have Mg. Okay, this is the two things we have, and the Mg is 5 centimeters in length. Okay, so the student is actually doing 5 experiments. What's happening? In experiment 1, rinse a burette with distilled water and then with dilute sulfuric acid. This is what we're doing. Oh, so small. Rinse with water and with distilled water, and then with dilute sulfuric acid. Fill the burette with sulfuric acid, and you need to run some of the dilute sulfuric acid out of the burette. Done? So that the level of the sulfuric acid is on the 0.0 centimeter cube mark. Use the burette to add 30 centimeter cube of dilute sulfuric acid to a boiling tube. Use a thermometer to measure the initial temperature of the acid. It is important when you're carrying out any experiment that's related to temperature change, you record the initial temperature. Okay. Add a coil of magnesium ribbon to the boiling tube. At the same time, start a stopwatch. So I'm going to continually stir the contents of the boiling tube using the thermometer. After 1 minute, measure the temperature of the mixture in the boiling tube. Record this temperature. This is what we've done. Okay, let's go to the next one. Experiment 2. Same steps, so I'm not going to read that. Use a burette to add 25 centimeter cubes of dilute sulfuric acid to a new boiling tube. So now we have changed to 25 centimeter cubes. Okay, from 50 to 25. So measure the initial temperature of the acid, and all the things are same. Okay, all the things are same. Everything done. Then we're doing the same experiment, but now we're reducing the amount we're using. Now we're using 20 centimeter cube to 15 and then 10. So we're reducing the amount of dilute sulfuric acid each single time instead of 25 centimeter cube. This is what we need to keep in mind. Okay. Now we have volume of dilute sulfuric acid, and now we need to record the initial temperature and then temperature after 1 minute and the temperature increase. Okay, so the first is 21.0. Actually, always write 21.0. If you don't write that, you will not receive a mark because you're supposed to make everything in chemistry paper 6 to one decimal place, especially this one. And this is going to be 21.5 since it's in the middle. 21.5 again. This is 22.0. And this is also 22.0. Simple. Now this is temperature after 1 minute, which is going to be 29.0, 36.5. This is 35, this is 36.5. And then we have 33.5. This is going to be 38.5. Simple. Then this is 46.0. Now the temperature increase, you're gonna calculate this. How do you calculate this? You're gonna use the help of your calculator, and you're gonna subtract temperature after 1 minute with the initial temperature. Okay, so now I have calculated the temperature increase. This is what I've been getting. Now let's move on to the graph. Now, figure 2.1, complete a suitable scale on the y-axis and plot the results from experiment 1 to 5 and draw a line of best fit. Now draw a line of best fit, and that's what we've been given. We have volume of dilute sulfuric acid on the x-axis. On the y-axis, we have the temperature increase. Now, you need to find a suitable scale for this. So we have 8 to 24. Let me think about this. Okay, so I'm just gonna go up by 5 every time. So 5, since they have done to one decimal place, I'm also gonna do that. So 5.0. All right, then 10.0, 15.0, and then 20.0, and then 25.0. I'm going up by 5 every single time. This is what the scale I've chosen. You have to choose it in a sensible way. Alright, so this is the scale I've chosen. Now we're gonna look at that and use it. Now the volume of dilute sulfuric acid is 30. At 30, the temperature increase I'm getting, this is gonna be 8. And at 8, it's 30. So what I'm gonna do is take my ruler, and where 30 is, I'm just gonna draw. Alright, this is where my 30 is, so I'm just gonna draw. In chemistry, you have two ways of drawing. Either you can just draw an X in a circle, or you can just draw an X. Totally up to you, but I prefer doing it like that. It's easier. Alright. Okay. Next is at 15. Okay, 25. At 25, it's gonna be 15. So your 25 is here. So for 15 is here. So at 15 it's 25. I'm just gonna draw an X here. Alright, got that. Then we have 12 and 20. So at 20 it's 12, which is gonna be 12 is here. So I'm just gonna draw a line here. Alright. This is what I'm getting, and then 16.5, it's 15. So 15, it's gonna be 16.5. So 16.5 here. Right, 15 is there, so I'm just gonna draw a cross here. And at 24, it's 10. So 10 is here, and at 24, it's gonna be 24 is right here. So it's gonna be my first one. Alright, we've drawn the scale. Now I'm pretty sure this is easy to do on a paper because you have to zoom in a lot, but it's okay. Now what you're gonna do is draw a line of best fit. You can just bring out your ruler and make things equally on each side. Explain why the temperature increase changes as the volume of dilute sulfuric acid changes. So what you can say is, as you're adding more, as you're using more volume of dilute sulfuric acid, the lower the temperature is going. Like if you see at 25 centimeter cube, the temperature is 15. But the more higher you go, it's still decreasing. The temperature increase is getting lower. So you can say more volume of acid is lowering the temperature. Why is it lowering the temperature? It's lowering the temperature because the acid is in excess. Excess means it's more than needed. So the acid is in excess. Simple as that. Pretty easy. Okay, that's done. Now let's move on to the next one. Extrapolate the line of the best fit over a graph in figure 2.1 to deduce the temperature increase of 33 centimeter cube is used here. So if I extrapolate my graph, the line I'm getting is at 0 degrees Celsius. So this is my 33.0. So I'm getting 0 degrees Celsius. So my temperature increase is 0 degrees Celsius. That's the answer. Okay. The investigation is repeated using 2.5 centimeter lengths of coiled magnesium ribbons instead of 5 centimeter lengths. Sketch a line to show the results you would expect. Label this line L. Now, as we know, if you're using a smaller length of this, it's gonna reduce the volume needed, right? It's gonna make everything go half. So therefore, this is like a limiting limiting reactant. So your product will be lesser if you use less amount of reactant. So I can just copy this line actually and make it smaller. So anywhere below this line, you can draw another line that's half of this, and this is gonna show that the products will decrease as your length of the coiled magnesium ribbon is decreasing. Okay, give a reason why a burette is why a burette rather than a measuring cylinder is used to measure the volume of sulfuric acid. Now, as we know, a burette out of a volumetric pipette, a measuring cylinder. Burette is the actual one which is the best for using in experiments. Burette is more accurate, or I can say it gives more accurate readings. Out of all those equipment you can use this one because it's more accurate. Okay. Explain why the contents of boiling tube are stirred during the experiment. Now, this is a very basic knowledge. when you have, let's say you have a cup. Okay, in the cup I added some coffee, and now I have a spoon I'm stirring it with. Sorry, don't mind my drawing. I'm just gonna make the spoon like this. When I'm stirring the mixture with a spoon, the main concept of stirring is to dissolve or to mix my ingredients, right? So you can say to mix the contents, and you can say to dissolve them faster, because it dissolves faster, or and the particles actually spread out properly. They're evenly spread out, so to dissolve them faster, you can see that, or to evenly spread them out. Okay, describe what changes the apparatus that will give more accurate results. One of the things I would like to tell here before is that we're using to investigate about a temperature change. One thing you need to know about when you're doing a temperature change is that in temperature changes, you're supposed to have something that will reduce the amount of heat loss, because you need maximum amount of heat. What you can use is change the apparatus. You can use an insulated boiling tube, or you can cover the boiling tube with a lid to reduce the heat loss, so minimize heat loss. Or you can say use a polystyrene cup. Okay, I'm gonna write use a polystyrene cup with a lid. This is gonna cause insulation. So the explanation you can say is that to reduce heat loss. All right, it will reduce the amount of heat lost to the environment. Sorry, not the environment, in the experiment. So it will cause maximum heat to be inside your polystyrene cup. Okay, now this is a very simple part. It's very easy to gain 9 marks from all of this. So let me teach you an easy way. It's pretty easy because you need to refer to those quantitative analysis notes. Now let's read the question. A student tests two substances, solution A and solution B. Now we're knowing about the solution on test on solution A. So solution A is aqueous iron 3 nitrate. Okay, the student divides solution A into 3 approximate equal portions. So we have, what do we have? Sorry, iron 3 nitrate. So we have iron 3 nitrate. Now this is divided into 3 equal parts. Okay, 3 equal parts. Okay, I'm gonna make a box here for every single one. Alright, so these are the tests being conducted on this compound. Okay, now the student divides them into 3 equal portions. That's what we read. So the first portion of solution A, student adds aqueous ammonia dropwise and then in excess. So we're adding ammonia, which is NH3. This is what we added, dropwise. Okay, so we're gonna go back to those notes we have. So because ammonia, what was iron 3 nitrate. Now we have iron and nitrate, and we're adding aqueous ammonia. Now nitrate. Now if we add iron, if we add aqueous ammonia to iron, it's going to give us a red-brown precipitate, which is insoluble in excess. Okay, this is the answer you're going to write. So when you're adding it drop-wise, is that given? So you're going to just write red-brown precipitate, which is insoluble in excess. So you're going to write, it forms a red-brown precipitate, which is insoluble in excess. This is what you're going to write. All right. Okay. To the second portion of solution A, the student added aqueous sodium hydroxide. I think we wrote NaOH. We wrote that. Okay. Now, what are the observations? This is going to be, going to go back to those notes again. We know that we're adding to iron, which is going to be insoluble in excess. Insoluble in excess. So just going to repeat the same part and write it down. Okay, so I'm just gonna copy this. All right. Insoluble in excess. Now, to the product formed in BI, the student adds a small piece of aluminium foil. The student gently warms the mixture to form and tests any gas produced. Now, one thing you need to know. I'm gonna go back to the anions test. We add aluminium foil after adding sodium hydroxide, and then warm carefully. It's for nitrate. We do have a nitrate ion. So when you put aqueous sodium hydroxide and then add aluminium foil and warm it gently, you get an ammonia produced, ammonia gas. So we're gonna write ammonia okay, never mind. This is observation. So they performed tests to see any gases produced. Now, as we know, for ammonia, it turns damp red litmus paper damp red litmus paper blue. This is the observation you will get. Now we need to identify the gas, which is ammonia gas. Ammonia, not ammonium. You need to know the difference between ammonia. Ammonia is NH3, ammonium is NH4. Totally two different things. Okay, to the third portion of solution A, student adds about 1 centimeter cube of dilute nitric acid followed by a few drops of aqueous barium nitrate. Now this is the test for sulfate ions. Now we don't have sulfate ions present in our solution because it is iron 3 nitrate. So what are you going to write? You'll not say an answer for that. You'll just write no change, since there is not going to be any changes because there are no SO4 2 minus ions in there anyway. So your answer is going to be no change. That's all. Okay. Students will assess and the student's observation for solid B. And we're testing solid B. So we did a flame test on that. We get a light green flame color. Go back to those notes. Light green flame color is barium. So the way I like to do it is, I'm just going to write BA here. So BA 2+. This is the ion present. Add the remaining solid to B to continue dilute hydrochloric acid and test any gas to produce effervescence and colorless solution forms. Lime water turns milky. Now this refers back to carbon dioxide gas. So this is going to be effervescence and a colorless solution forms. So you can see lime water turns milky. It's for carbon dioxide gas. So carbon dioxide and effervescence, carbon dioxide is produced. So this is a carbonate ion. So this is going to be CO3 minus. So your answer is going to identify the gas produced, which is going to be carbon dioxide. Carbon dioxide is produced in the second part. And we're going to name the solid B as barium carbonate. Okay? Barium carbonate. Alright. Okay, so the next part, duralumin is an alloy. So this is duralumin is an alloy containing a mixture of aluminium, copper, magnesium, and manganese only. Contains these four things. Alright? We have a table about these four metals in the duralumin. Okay? Okay. Now, when we have a reaction with HCl, aluminium will react, copper does not react. Then we react to form a soluble sulfur magnesium and quickly react to form a soluble sulfur manganese. And for dilute nitric acid, only aluminium does not react, whereas everything else does react. So plan an investigation to find the percentage by mass of aluminium in the sample of duralumin. Your plan must include how you will calculate the percentage mass of aluminium in duralumin. You're provided with power sample of aluminium duralumin, dilute hydrochloric acid, dilute nitric acid, distilled water, and common laboratory apparatus. Now, how you can do this is pretty simple. Alright, way I'm going to think about this is we need to know the percentage by mass of aluminium. So what we're going to do is that not use dilute hydrochloric acid, instead use dilute nitric acid, since it is the only one which is not reacting with aluminium, whereas everything else is reacting. So what you can do is just react copper, magnesium, and manganese with all of these with nitric acid, and dilute, whereas aluminium will not react with dilute nitric acid and will just stay inside. So what you can do is then filter it out, add known masses of these powder samples into dilute nitric acid, and then react them. When they react together, aluminium is just going to be left there inside since it does not react with nitric acid. So what you're going to do next is that you're going to obtain that nitric acid by filtering the solution and collecting the residue, and then washing it with distilled water, rinsing it with distilled water, and then collecting that sample of aluminium, that powder sample, and then you're going to weigh it using a digital weighing balance. And after weighing it, how will you calculate the percentage by mass? Now there is a formula to calculate percentage by mass. What you're going to do is you're going to write percentage is equal to mass, your mass of aluminium over mass of the duralumin. So I'm just going to write the mass of alloy times it by 100. Include this formula in your conclusion to get that extra mark to get a 6 out of 6, and rest is pretty much simple.